Hey guys, welcome to the first ever video on my YouTube channel. This is gonna be about my favorite topic in maths, which is calculus. Of course, it's very interesting. So today we'll be looking at how to derive the power rule. So we all know that when f of x, wait, let me just change the thickness of my pen real quick. Okay. We all know when f of x, f of x equals x power n, f dash of x, which is another way of writing dy by dx. So let me just put that in brackets. Dy by dx. F dash of x equals, we bring down the power, multiply it, so we have n at the front, and now we have x power n, but then we have to minus 1 from the power, so we have that. But how did they actually come up with this? Because ancient mathematicians, how did they have the tools to think about this and make it easy for us to learn it in class? So how they did it is they used the definition of a derivative. So you guys should have learned that the definition of a derivative is f dash of x equals the limit as h goes to 0 of f of x plus h minus f of x all over h. So now where this comes from is really from the graph of any function. So let's say we have a quadratic graph here, f of x equals x squared. So now what we do is, let's say we want the gradient at this point here. So we have the gradient like this, and we want to find the gradient without using calculus, because remember, ancient mathematicians didn't have calculus, they had to invent it. And so what we do is we take a point that's very close to the original point that we thought of to take the gradient, and we take the gradient between those 2 points, and you can see that the gradient is kind of similar but not really the same. So what we have now is 2 points that are connected by a curve, and we can see that there's a change in their x and a change in their y. So let's call the change in x h, because why not? Algebra is all about just random letters assigned to variables. And if we say this is h, that means that let's say this point here has x coordinate x, and so this point here would have x plus h as its x coordinate. So now, remember the formula for a gradient? M equals, pause the video and like say it out loud, I guess, or say it in your head, is y2 minus y1 over x2 minus x1. So this basically says the change in y divided by the change in x, or the rise over run, or whatever you want to call it. And so we want y2 here. So y2 is the top y value, which is, if we look back to our equation, f of x, but the x value is x plus h. So we have to plug in x plus h where x is. So this x value would be f of x plus h. And this x value would just be f of x, because the x value is x. And now we can plug the values into the equation. Let me just scroll down a little bit. We can plug the values into the equation. Yeah, okay. So when we plug it in, we get m equals f of x plus h, because remember, y2 is the top y value, which is f of x plus h, and minus y1 is f of x, so f of x, and all divided by, this is x2 minus x1, so this minus that, so x plus h minus x. So now what we get is, when we simplify this, remember we can't simplify the top to f of h because we don't know what the function is. If the function was x squared, you can't say x plus h the whole square minus x squared is h squared. So that doesn't work, so we can't simplify that. So we have f of x plus h minus f of x all over, and the x's cancel, so we have just h at the bottom. And so this one is a useful point when taking derivatives, but we don't have an accurate derivative because when we take the derivative here, it's this line as opposed to something like this line. So what we want to do is bring this point closer and closer and closer to this point here. And we do that by limiting the h, which is the distance between the x's. And that is the limit as h goes to 0. So we say the distance between the points is basically 0 because we're taking the limit as the distance goes to 0, and we just have the same equation over here. And so that's how they derived the definition of the derivative. And now we want to use this derivative definition to get a formula for the power rule. And how we do that is the following. Let's see. So we want f dash of x, where f of x equals x power n. Put some curly brackets to seem fancy. Look at those, amazing. So now we have f dash of x equals, now we look back to the equation here or here. So this one, let's look at this one because it's closer. And so f of x plus h, we can see that f of x is x power n. So naturally f of x plus h has to be x plus h where the x is. So it is x plus h all power n. And minus f of x is just x power n. So x power n all over h. And can I separate this? Let's see. I think so. Okay. Anyways. Okay, so now we want to expand this using our beloved binomial expansion. And what we get is... Oh, I forgot the limit. Oh no. Key part of the definition. The limit. F dash of x equals the limit as h goes to 0. So now we have the limit as h goes to 0, the same thing, and we have, as we remember, it's nc0 times x power n plus, let me just erase this to have enough space. So we have x power n times nc0, and then we have nc1 times x power n minus 1, and multiplied by h power 1. And then we have nc2 times x power n minus 2 times h squared, and so on. So we have many terms depending on what the value of n is, but generally we have a continuing sequence until n goes to 0 at this place here. So we have that, and then we have minus x power n, and this is all over h. This is the fun part. This is where all the canceling happens. We have the limit as h goes to 0 of... Now we can see that nc0 is just 1. by definition. So x power n, let me just keep the curly or the square brackets, and NC1, if you remember the formula, if you remember the formula for combinations, so NCR equals, say it with me, n factorial divided by, what's the first term? R factorial times n, is it factorial? No, it's not. N minus R factorial. So when we have NC1, we have n factorial, because n is the same, divided by 1 factorial times n minus 1 factorial, which is, we can simplify this or expand this to see n times n minus 1 factorial as the properties of factorials. So we have this cancel, that cancel, so we have just n. It's always, NC1 is always n, even in the general sense. And now we have plus n x power n minus 1 times h, it's h, not n, plus, now NC2 is an interesting case because, just move this, oh wow, I actually did it, wow, incredible. Okay, so now we have NC2, we need to find what NC2 is. So, NC2, using the formula, of course, is n factorial divided by 2 factorial times n minus 2 factorial. And we can rewrite this as n times n minus 1 times n minus 2 factorial. So that and that cancel out, and we have n times n minus 1 all over 2 factorial, and this is just 2, so we can say this is n times n minus 1 over 2. So now we go back to our equation back here. We say n times n minus 1 over 2 times x power n minus 2 times h squared, and we have multiple terms after that. And we close the square brackets, and we have the same thing. Don't forget the x power n. Just because we finish the sequence doesn't mean we forget to include this. So we have this all over h. We see that we have one term common, which is this and that, and they're opposite signs, so they cancel out. Oh, what happened there? For some reason, a post-it note for some reason popped up. Okay, and that cancel because they're opposite signs. And now we have the limit as, oh, actually, we can also cancel out the h's. So we have h cancel here, and h squared cancel with this h, and so on. So now what we have is, so we have, let me erase the limit. So we have the limit as h goes to 0 of n x power n minus 1, because we canceled the h, there's no h anymore, plus, and this looks promising because remember, this is the formula for the power rule. So this is probably the right track, we'll see. And n minus 1 over 2 times x power, oops, what happened there? Oh no, it's lagging. Oh no. My worst fear. Okay, so erase that. We have n times n minus 1 over 2 times x power n minus 2 times h, and so on. So the important fact is that all these terms in this dot 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 all include h, so have h in some degree, so in some power. So that actually becomes an interesting fact because we remember at the start we said the limit as h goes to 0, which means that this h can effectively be 0. So this whole term goes to 0, and all of these terms cancel to 0. Or not cancel, technically, it's just, is it not going back? It's not undoing. Okay, anyways, okay, there it is. So we have that, and these all go to 0, and now we're left with, we can remove the limit because there's no h anymore, so this is just n times x power n minus 1, and we have our answer. Wow, incredible. We went through all that working just to get the power rule, and that's what mathematicians did, or I think that's what they did. I didn't really research on this topic. Um, and so yeah, this is how you derive the power rule. And you can do the same for something like f of x equals a x power n. When you go through the entire process again, you get a n x power n minus 1 because, or I should specify where a is a constant, because a can sometimes be how do I say this? A function of x, and that would require like product rule and other things that'll come up in a later video. And so yeah, it's very interesting how they derive the power rule, especially the derivative definition of the derivative. It's very how do I say it? It's very exciting per se. So yeah, please leave any comments to guide me on how I can improve these videos, and stay tuned for the next one, which will be on deriving the product rule. Thank you for watching, and I'll see you later.